Okay, in the previous section, 4.2, we talk about uh, mechanical kinetic energy and gravitational potential energy. Another form of a potential energy is elastic potential energy. So essentially, this is the energy stored in a spring. Okay. So to start with, work again. The basic definition of work is just force times displacement. But remember that force and displacement must be uh, parallel to each other. And according to Hooke's law, so this pertains to the forces in a spring. According to this particular law, that the magnitude of the force is just given by F is equals to Kx. So again, F here, where F is the magnitude of the force in Newton. Remember that we define in our different types of forces when we talk about different forces like the normal force, friction, tension force, one of which is the spring force, right? And remember that its direction, I emphasize here that this is just talking about its magnitude. Remember that the direction of the force exerted by a spring on an object will always be opposite to its displacement. So what I mean is that if you have a spring, if you're gonna stretch it out, you're gonna stretch the spring out. Remember, its force is inward. That means that you can feel that it will try to pull inward. But if you're gonna compress a spring, you can feel that the spring will try to push your hands outward. So the displacement is inward, the direction of the force is outward. Again, that is the uh, how we try to define the direction of your spring force. It is always opposite to the displacement. So displacement means when you try to displace your spring, either stretch it out or you try to compress it. So again, I'm just talking about the magnitude here. So at a certain uh, according to Hooke's law, the magnitude of the force is given by Kx. And what is that K? So K is the spring constant. So this is the spring constant in Newton per meter. So for different types of springs, you're gonna expect the spring constant K is different. And remember, the unit is Newton per meter. And X is just the displacement. So this is just displacement of the spring from its equilibrium position. Okay, so the unit here is in meter. So take note of the different units that you're using. Force must be in Newton. K is given in Newton per meter. And lastly, the X, which denotes the displacement, should be in meters. So that means that uh, if you will be using this formula here, try to remember that the force that the unit of the force is in Newton, and the spring constant is Newton per meter, as well as the displacement must be in meter. Because if they are not, you need to convert. So that means that if the force is in millinewton, so try to convert it to Newton. And other units also, although for the spring constant, I will not give you another unit for that. We've been only talking about the unit of force as Newton. But there are actually other units of force also. Dyne is actually a unit of force, but since we haven't talked about that one, so spring constant must be given, or if ever, will be given in Newton per meter. And lastly, for the displacement, we use the unit meter. Okay, so it's displacement from its equilibrium position. So when we say equilibrium position, that means that if you're not doing anything with the spring, so that would be its form. But when you try to press it downward, well, whatever is its distance that is being pressed down, that would be the value of x, and stretching it out. So that would also be the displacement. Okay, and we learned in the past that work, if we are given a force displacement graph, the area under its curve or under its graph is just equivalent to work. So the area under under a force displacement graph is the work. So we try to make use of this in order for us to get the expression for elastic potential energy. So let's take this example here. First example, Mr. Su is experimenting with a spring. He applies a force and notices the displacement of the spring from its equilibrium position. So determine the work done in stretching the spring 4.0 meters from its equilibrium position. So this is one way of actually knowing the force constant, K. So at different displacement, you try to place certain amount of force. So for these are the different points. So that means that if you're not applying anything, so that means that this is your equilibrium position. When you apply a force of 1 Newton, the spring displaces by 1 meter. And then if you're going to employ 2 newtons on that, well, the displacement is now 2 meters. And then if you place 3 newtons, it gives you a displacement of 3 meters, and so on and so forth. And then now you create this straight line graph. Okay, so we want to determine the work done in stretching the spring to 4 meters from its equilibrium position. So work done. And we know that the work done here is just equivalent to the area. So how would you get the area? Well, up to 4 meters, and then all of this is the work done. Okay, so this is the work done in stretching your spring from 0 to 4 meters. So this is the work. Okay, so the work done is just equivalent to the area. So which area is that one? That the one that is shaded by that yellow thing. So what is the area of that? Well, this particular figure that you created, this is a triangle. So this thing is a triangle. Okay, and the area of a triangle is given by 1/2. So area of the triangle is just 1/2 the base times its height. Okay, that is the area of a triangle. We get the area of the triangle by multiplying its base times the height divided by 2. So therefore, using that one, so this is work is equal to 1/2. Well, what is your base here? The base is just given by this one. That's the definition of the base, right? The distance from that point, the lower part of your triangle. So this would be the base. So what is the value of your base? Well, that's 4 meter. So that's your base. So that's my base, 4 meters. And now what's my height? Well, if you can see, what is this height here? The height is this one. And this height is 4 newtons. So therefore multiplied by 4 newtons. Okay. So if you can see, I'll just have to multiply everything and get the value of, that should be 8 Newton meter. But Newton meter is just equivalent to 8 joules. Okay. So therefore, the work done in stretching your spring is 8 joules. Okay. So according to Hooke's law, remember that this particular case, this is just an equation of a line, right? If you can remember in your, this is just an equation of a line. Wherein, if you can see, if you're gonna base in this graph here, that means that F is just directly proportional to this, the displacement. That means that according to Hooke's law, so whatever amount, if you're gonna increase the value of F, the value of X also increases by the same amount, because that's the characteristic of a straight line. So K is just a constant of proportionality, or your slope. So actually the slope of this one gives me the spring constant of the spring in this particular case. Okay. So so again, we observe that the area under the graph is a triangle. So let's try to get the expression for the elastic potential energy. Okay. So work, remember that we can also write the work in terms of energy. It's just E. Okay. And we know that the area work is just equivalent to the area of the triangle. So work, you can replace your work as A of triangle, okay, is equal to E. So again, already shown in the previous one that the work done is just equivalent to the area. Okay. And if you can see, area of the graph, since for a spring it follows Hooke's law, so you should always get this type of graph, a linear graph. Okay. So that is just the area of the triangle is just 1/2 base times height. But you can indicate there that the base and the height is just in terms of FD, or I'll just use X in this case. 1/2 Fx is equal to E. Okay. So therefore, I can rewrite this one as, I'm just going to write this one as E is equal to 1/2 Fx. Okay. So based on for a spring, remember that it follows Hooke's law. So that means that the force can be replaced with key x. So this is 1/2. So F is equal to kx. So this is kx times x. So I can replace my F with kx because again, I'm talking about the energy in a spring. In this case, so kx. And if you can see, I have 1/2 kx times kx. So remember that again, this is from Hooke's law. So I'm just gonna, this is from Hooke's law. Okay, that is coming from Hooke's law. So I can rewrite my E. Actually, energy stored in a spring is equivalent to 1/2 kx squared. Okay. So where k is just a spring constant, in, again, this is Newton per meter, and then x is the displacement of spring in meter, and then ES is just the elastic potential energy. Potential energy in Newton meter or joule. Okay. So if you can see, it's this particular equation, the final unit is also still in joule. So somehow that gives you an idea that indeed the answer of this one is energy, in terms of energy, because the final unit is joule. So actually, this is the expression for the elastic potential energy stored in a spring. So if you try to stretch it out, so there must be a corresponding energy to that, and that is called the elastic potential energy. Okay, and just try to remember the different units that you use there so that you can say that the final answer, if you are looking for the displacement, well, the final answer should be meter, as long as the value of K is in Newton per meter and the elastic potential energy is in joule. Okay, so again, over and over again, I try to repeat that one because this is very important, because if X is in terms of centimeters or millimeters or any other unit, remember that you cannot automatically say that your final answer is in joule. So you have to be consistent with your units. So just like in example number 2. So if you can see here, how much energy is stored in a spring that is stretched 10.0 centimeters if the spring constant is 25 Newton per meter. So you try to write your given and unknown. So identifying the given and the unknown. So the given here is K. So from the unit itself, you can identify that that would be your spring constant, 25 Newton per meter. And then the X, we use X for stretch out. So that pertains that it is being displaced by 10 centimeters. But if you can see, this is centimeter. But in our definition, when we try to define the expression for the elastic potential energy, we use the unit meter. So therefore, you need to convert this one to meter. So that would be 0.1, I believe. Yeah, 0.100 meter. Okay. And we are solving for how much energy. So again, you're talking about a spring here. So therefore, it should be ES. So that would be your question mark. Potential energy of the spring. Okay. So now for the solution. So you just have to use directly. You don't have to show this part here. You just have to go to the final expression for energy of the spring. Because anyway, that's your main question, right? Then 1/2 kx squared. So what you're gonna do is just substitute. Well, in solving for your elastic potential energy, all you need to have is the value of k and the value of x. So in this case, the two are given, so therefore you can just substitute those values. 25 times 0.1. So that gives me let's see, what's that? That would be 25 times 0.1. I forgot, it should be squared. So that would be power 2 and then times 0.5. So stored energy is 0.1. Well, those 125. Because anyway, this is a constant, so this is already part of, well, that is just a constant. So we're gonna read the number of significant figures from here. So 3, and then the unit would be joule automatically. Okay.